Hi everybody, Miss Mocano here, and today I wanted to give you a little bit of background information for our plate tectonics unit. That's going to help you with at least two assignments, the plate boundary lab as well as the plate tectonic lab. So let's start off with Alfred Wegener, who is an important scientist, German scientist. He was a meteorologist and climatologist, and he is credited for coming up with the hypothesis called continental drift. So let's see what that is all about. So Wegener noticed, as many people will, that if you look at continents on a map, for example, South America and Africa, a lot of times it seems like they fit together very closely, almost like pieces of a puzzle. So he noticed that. He also had a bunch of other evidence that led him to come up with this hypothesis of continental drift. Another piece of evidence that he had is that rocks and mountains on separate continents seem to fit together very well. So, for example, on both sides of the Atlantic, there were mountains found that had the same exact type of rock in them, same age, same kind of layering of the rock. And so it was interesting to Wegener, and it kind of raised some questions for him why you would find these similarities or almost exact same type of rocks and mountain formations so far apart. Another type of evidence he had was from fossils. So he ended up noticing that fossils of the same species were found, again, on completely different continents, very, very far apart. And a lot of times it would be species that were known not to be able to swim. So he couldn't explain it by saying, well, this animal must have lived, or this plant must have somehow made it across the water onto the other continent. That just wasn't, it wasn't plausible. So based on all these pieces of evidence, and you can you should do more research into this, because there's definitely a lot more to it than I am able to tell you here in a few short minutes. But Wegener hypothesized this hypothesis called continental drift. So continental drift says that about 300 million years ago, all of the continents that we know today had instead been coalesced or together in a single massive landmass called Pangaea, meaning all earth in Greek. And that this continent was at one point together, and then it started spreading apart and splitting apart, and has been splitting apart ever since. So that is continental drift. Unfortunately for Wegener, at the time, his idea was not accepted by most scientists, and he was actually ridiculed for it. And the big problem that he had was that he could not explain how exactly did this happen. How exactly is it possible for the continents to move together or move apart? How is that possible? He did come up with a couple of explanations. Unfortunately, they were wrong, so they ended up kind of discrediting him. He thought somehow a centrifugal force was involved. He thought that maybe the continents were kind of plowing through the crust of the earth, kind of like an icebreaker would plow through the ice. And unfortunately, neither one of these was correct. He ended up dying without the world having recognized his hypothesis as being correct. But his hypothesis did in time turn out to be true. So continental drift was in time proven to be correct. And there are several pieces of evidence, important pieces of evidence for it. But among them is seafloor spreading. So the fact that the floor of the sea floor of the ocean is actually spreading apart, and as well as alternating magnetic polarity. And how is this all happening? What is the mechanism driving this whole continental drift? Well, it is mantle convection. Mantle convection meaning these currents driven by the heat inside of the earth, currents as you can see in this image, going up and down, round and around. Well, those currents are what push up on the lithosphere. They push up on the crust of the earth, whether it's oceanic crust or continental crust, and they force it to move apart, and that's how the continents end up moving relative to each other. Eventually, a lot of research was done, and I'm going to let you guys go through this at your own pace. But eventually the ocean floor was mapped, and it was found that, like I said, the tectonic plates do in fact come together. They do in fact split apart, and the ocean floor was mapped, and it proved the hypothesis that Wegener came up with. I'm going to skip through and move on to the theory of plate tectonics, which arose based on Wegener's work. So plate tectonics explain how and why the continents move, and it also explains how a lot of features on Earth are actually created. So that's what we're going to look at next. So this map right here shows the Earth's plate tectonics. You can see they're all shown in different colors, and they all have their names. So for example, this is the Pacific tectonic plate, Australian plate right here, North American plate, and so on. Okay, so these are the tectonic plates. As you can see, the tectonic plates don't necessarily match up with only continents or only ocean. They include continents, they include water or ocean, so they can include all of that. They can include continental crust, oceanic crust, or both. As you can see from this image right here, and there will be more images coming up soon. For example, this image, which you will be conducting some work with, these plate tectonics have boundaries. And these boundaries are really, really important. There are 3 different types of boundaries that we're going to talk about. And what happens at these boundaries actually determines what features we can see on land or underwater. So, for example, the 3 different types of plate boundaries that we have are divergent, meaning they're moving away from each other, as you can see indicated by these arrows. Convergent meaning coming together. And transform, meaning they are moving past each other in opposite directions. Based on what is happening at what kind of boundary we can have different landform characteristics that happen. So for example, divergent boundary, meaning they're moving apart from each other, such as you can see on this map. It's actually showing you down here the key of the map. So divergent, we're looking for these arrows moving away from each other. So right here, the East Pacific Ridge, that is a divergent boundary. Here we can see the arrows moving towards each other. That would be a converging boundary. And then over here where you see these arrows moving parallel to each other but in opposite directions, that would be a transform boundary. And again, each of these boundaries has very specific features associated with it. And this is a summary of those features. For example, divergent boundary, that's where new crust is created. There's volcanic activity possible at those boundaries. For convergent, where they're coming together, a lot of times you will find volcanoes, earthquakes, mountain chains forming, as well as deep ocean trenches, and that is also where the old crust of the earth is recycled into new crust. And finally, at transform boundaries, a lot of times you will experience earthquakes at those kind of boundaries. Moving on, let's look a little bit more into depth at divergent boundaries. So right here you can see a type of divergent boundary. This is happening on land, as you can see, and you can see a volcano coming out as these 2 pieces of crust are moving away from each other, diverging from each other. You can see there is hot lava coming out, and that is a type of volcano that we can have at those boundaries. We can also have, when these boundaries occur underwater, seafloor spreading happens, and we can have, that's where we get new crust created, okay? Let's move on to the next slide. So a little bit more information, then I'm going to let you guys go at your own pace regarding divergent boundaries. A little bit of a map. All right, showing more divergent boundaries moving away from each other, and even more in Iceland, showing pieces of crust moving away from each other at divergent boundary. Next type of boundary we're talking about is convergent boundary, where the boundaries are coming together. This is where the old crust is destroyed and recycled into new crust. This is also where we get features such as deep ocean trenches. So these deep, deep trenches in the ocean happen at this type of boundary. We also get volcanoes happening at these boundaries, which you will explore in a lab, and very powerful earthquakes are also common features with these boundaries. Again, you'll be exploring this on your own in a lab. Let's keep moving. A little bit more information about these kind of boundaries and more locations of where these boundaries occur. We can also have mountains, and we often have mountains at these type of boundaries. And if you can imagine two pieces of crust coming together, pushing together, when they touch each other and when they come together, they still keep pushing. They have nowhere to go but up. Okay, so they're going to keep going up, and that is how mountains are formed. So those are typical features of convergent boundaries. And a little bit more information, Himalayas. And finally, moving on to transform boundaries. Transform boundaries. So now the plates are sliding past each other, parallel to each other, but in opposite directions, as you can see right here in this picture. A very famous example of a transform boundary is in California, the San Andreas Fault. And what happens when you have those two pieces of lithosphere moving past each other is that a lot of times they kind of get hung up on each other. So as they get hung up, there's a lot of stress building up. And eventually, when that stress is released, there is a tremendous event known as an earthquake that happens. So earthquakes are common at this type of boundary. And so here's a nice image summarizing the three different types of plate boundaries all in one image and showing what happens. And so let's finally spend just a couple of minutes talking about what exactly causes these plates, these tectonic plates, to move. And the phenomenon that is causing that to happen is called convection. Convection is what happens when you put a pot of water to boil on the stove. And at first nothing happens, but eventually as the water keeps heating, you can see those bubbles coming up and down, going in, up and down into the pot as the water starts to boil. So what is happening there is convection. The water, the fluid, is moving from the bottom of the pot where it's very, very hot because it's touching the burner to the top and back out, and you're seeing those bubbles. Well, the similar thing is happening inside the earth. Mantle convection, it is known as. As you know, temperature increases as you go deeper and deeper into the earth. And as temperature increases and that molten material inside the earth ends up having these convection currents, just like a pot of water on the stove. So let me show you guys right here. So this is what is shown by these red arrows. It is showing those currents. So basically hot fluid rising up and then coming back down and going in these currents like that end up pushing up on the lithosphere, on the crust above it, and moving it along. And that is the force that Wegener didn't know about. At his time, they didn't know about this kind of convection. They didn't know about the layers of the earth. So he couldn't have known about this. And that is unfortunately why his theory or his hypothesis was discredited, even though it later turned out that he was actually correct, and that continental drift is a fact and it happens. And that's how also plate tectonics came about. I hope this video was helpful to you guys, and I will see you in class.